So in the last video, we introduced the ways we can use derivatives to find velocity functions. In this video, we're going to try to use those techniques in a major way to do pretty much every kind of problem you can see in this section. Now, some problems might require a little bit of a combination of these techniques, but these are the fundamental techniques for position, velocity, and acceleration. So, we begin. Use the position function s of t equals blah of an object moving on a horizontal line, for examples 2 through 11. Distance units are measured in feet, and time units are measured in seconds. So we're going to keep in mind that our distance units are measured in feet, and our time units are measured in seconds. First, what is the initial position of the object? Well, if you go back to the chart at the beginning of Unit 3, or in the last video, we know that the initial position refers to the position at time 0. So we take 0 and we plug it into the position function. We substitute 0 for all the t values. So that would be 16 times 0 cubed minus 36 times 0 squared plus 24. And we see that the position, the initial position, is 24. And we know position is a distance type thing. So 24 feet. Done. What is the velocity of the object at t equals 1 second? Well, to find the velocity of the object, we're first going to have to find the derivative of position. And the derivative of position will be velocity because we're going to find how that position is changing, which is exactly what velocity is. So we take this derivative, green, we take this derivative v, v of t, 3 comes down, 3 times 16 is 48, t, 3 minus 1 is 2, minus 2 times 36 is 72, t, 2 minus 1 is 1, so we won't write the exponent. The derivative of 24 is 0, because 24 is a constant. So now I have this velocity function, and it's going to be a really important function, so we're going to keep track of it. But this problem asks me to actually find the velocity of the object at 1 second. So that would be v of 1, which is plugging 1 into this function. And we have 48 minus 72, which is negative 24. And the units for velocity, this is really important, if you haven't known this before in like a physics class, the units for velocity will be units of distance over the units in time. Now, the reason for that is because it's the rate of change of a position function. So it's going to be the change in position over the change in time. So position units over time units. Done. What is the speed of the object at t equals 1 second? Now every year on tests in this topic, people want to write s of 1 for the speed at 1. That is completely incorrect. S is already declared as the position function. So we're never, ever, ever going to write S for the speed function. Instead, we're going to usually use a sloppy notation, speed of 1 will equal the absolute value of the velocity at time 1. Because speed is the absolute value of velocity. So it'll be the absolute value of negative 24, which is just positive 24 feet per second. nothing's happened. We just took the absolute value, so the units for speed are going to be the same as units of velocity, but we're just ignoring the sign. Now, before we go on, I'm going to point out, to repeat it as much as possible, that the sign for velocity is telling us a direction component of the velocity. Because velocity is how we find the direction of this particle, or this object. The speed is saying, ignore the direction, I just want to know how fast it's going. It's going 24 feet per second. However, the object is moving 24 feet per second, and then that negative sign means to the left. So, if we're moving 24 feet per second to the left, the velocity would be negative. If we're moving 24 feet per second to the right, the velocity would be positive. Because the velocity is how we find the direction. Moving right along. So I've put the velocity function up here so we can continue to use it. Because the next question we're going to ask, is what is the acceleration of the object at 1 second? So to find the acceleration, our first step will be to take the derivative of velocity. Because acceleration is the derivative of velocity. Acceleration is the rate of change of velocity. So the acceleration function here, 2 times 48 is 96. Subtract 1 from the exponent, we get t. The derivative of negative 72t is negative 72. Again, if that gives you trouble, it's a line, it's a slope. The slope of the line is just negative 72 because derivative is also the slope. So that's the acceleration, and we can find the acceleration at time 1 to be 96 times 1 minus 72, and to simplify that, we get 24 also. Now again, it doesn't have to work out to be 24 every single time. That's just a weird anomaly in this problem. I'm going to emphasize the units on this though. It's a different kind of 24. So much like the units for velocity were distance units over time units, because velocity was the rate of change of position, because acceleration is the rate of change of velocity, its units will be velocity units, feet per second, divided by time units, which is seconds. Now, a lot of people think this is inelegant. It's feet per second. So most physicists, most mathematicians, end up writing 24 feet per second squared. Because you divide feet per second by second, you're multiplying by the reciprocal, 1 over a second. So we get this. Now, I don't care which one you use, but be careful that this is not feet per second, which is what many students write on their tests. When is the object at rest? So now we finally get into an interesting question. Being at rest, what does this mean? So at rest means I'm not moving. And not moving is only one of the three functions. Not moving means our velocity equals 0. And that's the key equation here. It does not mean the position equals 0. The position equals 0 will just mean you are 0 feet from the point of interest, the point where we're measuring from. You can still be moving, even if you're not right where I'm measuring. Acceleration equals 0 is the other major distractor here. But acceleration is about how movement is changing. So while this is weird, you can be hurtling through space at 1,000,000 miles per second and have a 0 acceleration. It just means you're not accelerating currently, you're still moving. However, you can be not moving at rest and have a positive acceleration. So when you watch the launch of a space shuttle, the rocket for an instant is not moving, even though a giant jet of fire is shooting out from the thrusters. And that apparent pause while it's accelerating is the fact that its velocity is still 0 for that instant. So usually students realize that something has to be 0. In this case, it is the velocity. So we're just going to set up that equation. We're going to write v of t equals 0, showing that that's what we're trying to solve. We replace v of t by what we know it is. And to solve an equation like this, we're going to use factoring. The greatest common factor of these two is 24t, which will leave a factor of 2t minus 3. And so we have two solutions. We have t equals 0 and t equals 3 halves. And these are both going to be measured in seconds. That's all there is to it. Use the position function, and now we have two other functions to discuss whether the object is moving right or whether the object is moving left. Now, this is a key skill. This is a skill that will be very much used in Chapter 4 in every single lesson almost. Please pay attention to what we're doing here. So object moving right, and if you watch the introduction video, we covered this in there. Moving right will be the idea that the velocity of the object is greater than 0. Whereas moving left will be the idea that the velocity of the object is less than 0. Now, in pre-calculus, you should have came up with this idea of a function inequality. These are both examples of function inequalities. We are trying to find out when this function will switch from being positive to negative or negative to positive. This has a very few steps, and they're very important. So when we're solving a function inequality, this is all we have to do. Our first step will be to find the zeros. So to find the zeros, we're talking about setting up the equation v of t equals 0. Now in the last example, we found out that that was when t equals 3 halves and t equals 0. Those are the two zeros. If you haven't already done this, that would be the first step, but we just did that in example 6. Step 2, make a number line. So it's real simple. We make a line. Pretty good line. Pretty proud of that. V of t, we label it so everyone's clear on what function we're doing. We put the two zeros on this number line in order. And then we're going to test the sign on that number line by plugging in test values into the velocity function. So for instance, between 0 and 3 halves, we're going to check sine of v of 1. That's what we're doing. We're going to check the sign of velocity when t equals 1. You can do this any number of ways. One way would be to go look at this function, where you would say, oh, it's 48 minus 72. 48 minus 72 is some negative number. In fact, we know it's negative 24. We actually did that in part 1. You could look at the factored version. So the factored version of v is v of t equals 24t 2t minus 3 times 2t minus 3. Plugging in 1 here gives me something positive. Plugging in 1 here gives me something negative. A positive times a negative is a negative. Easy. Over here, we're going to try a value greater than 3/2. The easiest thing to check that's greater than 3/2 is 2. Now, usually it's easier to use the factored value, and this is why. Plugging in 2 here can be quite messy. The student has to think about what 2 squared is, or 4 times 48 is some large number, and 2 times 72 is another large number. But in here it gets kind of clear, because we're using the idea that we know how positives and negatives combine with multiplication to make other signed numbers. So 2 in here would give us positive 48. 2 in here would give us a positive number as well, positive 1. Positive times a positive is a positive. One last one. Over here we have to use a number like negative 1. Trying this out again. 24 times negative 1 is a negative number. 2 times negative 1 minus 3 is also a negative. So now we have a negative times a negative, and we get a positive. So, what do these signs tell us? To put it all together, these are telling us the signs of velocity. So a plus sign means the velocity is positive, and a negative sign means the velocity is negative. Since we were looking for where the velocity is positive, for it to be moving right, now I know we're talking about t less than 0 and t greater than 3/2. These are both seconds. You could also label an interval notation from negative infinity to 0 seconds and from 3/2 to infinity. 3/2 seconds to infinity. A lot of students get troubled by having negative time. I want to emphasize negative time simply refers to time before the experiment started. This does not make sense in some cases. If I were to walk up to the Grand Canyon and throw a ball in the air and watch it fall, it would not make sense to ask me what the velocity of the ball was prior to me throwing it, because that was a very different function. However, if we're talking about a small particle that's been flying around since before humanity ever existed with the same position function, then it totally makes sense to ask, well, what was it doing before humanity existed? It's like rewinding the clock. This is how we discover how the solar system is formed. We rewind the laws of planetary motion and see where these heavenly bodies came from. Similarly, when we're looking where velocity is negative, we have this interval. So we're talking about t as being between 3/2 seconds and 0 seconds. And it's usually easiest to write this in interval notation, 0 to 3/2. In terms of whether we want these intervals to be closed or open, that's actually a subject of debate. I will prefer to write them always with open, and I would prefer you to write them with always open as well. The AP test will give credit for open, it will give credit for close in these cases, not if you close infinity, but in general, it would be We can say the particle is still moving left and right at 3/2. The particle is moving left and right at 0. Now, I don't agree with that philosophically. I think we mean that the particle is not moving left, nor is it moving right, so they should both be excluded. So just use open intervals, and you'll be safe. Stay safe out there. Sorry. So, when is the velocity of the object equal to 54 seconds? Now this spells it out quite clearly to me, but if you get confused, we are not plugging in 54 into the velocity function. Instead, we're asking, where is my velocity function equal to 54 seconds? And at this point, we'll use a calculator trick. If you want to practice the calculator, you should take it out now, pause the video, try it out. We're going to be plugging this in as y1. This in as y2. And find the intersections. That's usually the easiest way for students to do this. So here's my little emulator. I'm going to go to the y equals menu. I have a nice color calculator today. I'm going to plug in 48x squared. I know it says t. The calculator doesn't really care. And in this mode, we have to use x. It's just the human label. Minus 72x. And we're going to look for where this number or this function will meet this line. Now I know this is a horizontal line, and I know this is a nice, just going to be parabola. I know where this line is in terms of the window setting. We're going to hope our x min and x max don't have to change. Most of the time on the AP test, they give you values that fit into this nice window. So instead, we're going to go down here to change y min and y max. So let's try to use 10 lower than 54 for our min, and 10 bigger than 54 for our max, 64. Graph it. Wait. So there goes my parabola in a lovely shade of blue. And here comes my horizontal line in the lovely shade of red. Now, it looks like my computer is having a horrible slowdown, but we'll just live with that. So we see 2 points of intersection, and as I told you, both are going to be in this nice default window. Because I know this kind of function, a quadratic function is a parabola, I know I don't need to worry about other intersections happening outside this little box. So we're going to try to find out where these two cross. So we use second, trace, and we're going to use 5, the intersect. So now they're asking you, which is my first curve? So it's hard to see which function we're on. My calculator tells me right up here, we're on y1. You can scroll around and see, and try to see what's happening, but either way, our cursor is off the screen until we get to about 61. You might never find your cursor, but at least I was able to find it. This is my first curve. I'll hit enter. Here's my second curve. I'm on the horizontal line, y2 equals 54. And if I go left and right, you can see that I'm tracing out that line. Enter. I want to use that as a curve. Where do I guess the intersection is? Right around here. Enter. And we get this as our timestamp. This is a time value, and as we see, this is where the velocity equals 54. We know this intersection has to happen where they have the same x and the same y, so we knew the y value had to be 54. So I'm going to write this down to 3 decimal accuracy. Now on the AP test, you don't have to write this down. By this I mean they'll find the intersections here. You do have to write this equation down. If all you wrote down was this answer, negative 0.549 seconds, it's called a naked or a bald answer. And you do not get credit for that. You might not get any credit, you might get 1 point. This is worth something, please write this down. Second, calc 5 intersection, we're starting up here. I want to go over there. So I'm watching this. My y value is telling me where off the screen I am. And we're looking for this value to return to a number like 54. Or 54 thereabouts. Oh, look, 44, 63. It doesn't really matter at that point. That looks like around the intersection. Enter, enter. And there you find the second intersection to be at 2.049 seconds. And that's all there is to it. If you need help with the calculator, please come in and see me. I'd love to help you work it out better. Hopefully these videos give you a chance to see me working it out more in detail than I can in class sometimes. Displacement. So the displacement of the object will be based purely on the time interval. Displacement needs to mean position to you. So we're going to look at S of 2, the final position, minus S of 0, the initial position. S of 2, 16 times 2 cubed, minus 36 times 2 squared, plus 24, minus S of 0, which we'll use in parentheses, 16 times 0 cubed, plus, minus, careful, 36 times 0 squared, plus 24. Now, in general, you want to feel free to use your brain to recognize that this whole expression will just work out to be 24 when you plug in 0. But this will get just as much credit as that. So we're talking about 16 times 8 minus 36 times 4 plus 24 minus, and all that worked out to be 24, like I said. So we're talking about 128 minus 144, which equals negative 16. And what kind of units are we going to use? We're going to use feet, because again, this is a distance type thing. And what does this mean? A displacement is measuring how far you are off the initial position. So if in the analogy I was using earlier with my car, a displacement would mean that the car was 16 feet to the left of where it was initially. So, you go into when you go to school, you see my car parked in one spot, and then you leave school, you see my car parked in the other spot. It's 16 feet to the left of where you saw it parked last. So that's what that means. The negative sign means 16 feet to the left of the initial position. That's it. If it was a positive 16, we would say 16 feet to the right. If it was 0, we would say it doesn't differ from its initial position. And then usually whenever I ask you about displacement, I will follow it up with a question of the total distance. Now here, we need to take into account the direction everything is moving. So here, when we take into account the direction everything is moving, our total distance traveled between 0 and 2 seconds, we'll have to use the fact that, again, the direction of the particle changed at 3/2. So whenever you see the words total distance, whether you've done it or not, it will require that you use, first step, find the zeros of V of t. What I mean is V of t equals 0. And again, we did this when t equals 0 and 3/2. That's true for this problem. It's not true for every problem. So we first find the zeros of V of t. Then find position at endpoints and velocity zeros. Between the endpoints. So in this case, the endpoints are 0 and 2. And we're going to find out 3/2 because 3/2 is between 0 and 2. This usually leads to students asking, but what if we found other ones that weren't between 0 and 2? And we wouldn't check. If we found 0,18 instead of 3/2, we would only find the position at S of 0 and the position S of 2. If we found 8 zeros and all of them were between 0 and 2, we would have to check each of those 8 zeros and we would cry our little eyes out. So here we go. S of 0, which happens to be 24 feet. We found this a bunch of times by now. S of 3/2, because 3/2 is where a 0 velocity, endpoint, velocity equals 0, endpoint, be S of 2. S of 2, we kind of found this in the last problem. It would just be this plus 24, because we did 24 minus 24. So S of 2 is actually going to be 8 feet. And here we have 3/2 cubed. It's kind of complicated. It's really just 27 over 8 times 16 is 54. 54 times minus 81. So either way, you get negative 3 feet. And trust me on that. So now, all we have to do, step 3, calculate distances. So how far have we gone from -3 all the way to 27? Well, that would just be 24 minus -3. We're always going to do the big number minus the smaller number, which will be 27 feet. And here we're going to do 8 minus -3, the bigger number minus the smaller number, and we get 11 feet. So the total distance, TD, equals 27 plus 11, which which is 38 feet. Now, why does this work? Why does this method work? Now, I saw some people drawing this on their tests. I would not recommend doing this, but it will help you understand what happened. So we're traveling on a horizontal line. We're a little ant, we're a little tightrope walker, whatever. We start out at 24 feet to the right of the midpoint, or whatever you want to think, to the right of the position where we're calling 0. That ant starts off at 24 feet at t equals 0. The ant then travels all the way to 3 feet to the left of where we're observing. Negative 3 feet. Because he's to the left of where we are observing. And all that time he was moving left. Finally, the ant arrives 8 feet to the left of where we are observing. The scale on this is wildly whacked out. And we're asking, how far has that ant traveled? By separating out into v equals 0, we found out portions of time where we are certain the velocity is not changing. So this change was 27 feet left. We walked 27 feet to the left, 24 minus negative 3. And then he walked, I don't know why that keeps popping up. How many feet to the right? 11 feet. I'm going to draw it up there. "11 feet right." So why this method works is we've broken it up into chunks of time where we know for a fact he's moving in one direction, because the zeros of velocity are the only times when that direction could change. So while this might be useful to you, I highly recommend you learning how to do it just using this kind of analysis. So we found the zeros of v of t, we found the positions at each of those times, and then we calculated the distances between those positions. And that's it for this big example. Thanks for your attention. Bye-bye for now.